So coming off of the last video, what I want to do now is kind of tweak and fine-tune and look at the more nuanced details of controlling how these objects are forced to collide, um, and even if time permits, look at multiple objects and making them collide by their center of mass instead of just the distance between two objects, where things get a little bit more complicated. So if we look at the script running as is, you can see they collide after something like 2 seconds. But what if you want to change that? So coming back to our script, which was made in the last video, first thing I have in mind is to make a function which will tell us how long it took for our sphere 1, where the script lives, to collide with anything, whether it's the floor or another sphere. So we'll make a function which returns nothing or void, and I'll name it, I think this is the built-in on collision enter. Yeah. So private means it's not accessible to other objects in the scene, which we don't need it to be. It's just measuring when this object collides with something. And the function is a built-in on collision enter, and then it takes in a collision type with the name collision. I could change this to anything like collision A, B, or whatever, but whatever that name is what is used to access information about it. So effectively this function is saying when the object that this script is attached to collides with something, do this, and this is this. And again, the thing that this function is attached to is sphere 1, because when I click sphere 1 in the scene, you see come together the script here. So what we want to do, just as a first attempt, is just print out some information. So we'll say collision detected at, and then we'll say time.time. Time.time is the current time, starting from 0 when you started the game, and to string converts that to a string so I can concatenate it to the other string text. And then in addition to that, we'll say with, and here we'll say what the other object was that it collided with. So collision, again, is this modular name that gives you the ID of the collision object itself. Dot accesses its contents, and collider is a thing within that object, and even within collider there's a thing called name. So this will tell us the name of the thing it collided with when it collides. Okay, so if I save that, go into the console and let this play again, we should see collisions and when they happen. Nice. So this red sphere 1 object collided with the floor at 0.84 seconds and collided with sphere 2 at 1.86 seconds. If we move it, let it hit the floor again, there's 2 more collisions detected. So that's working nicely. Floor, sphere 2, nice. So what I want to look at now is changing the nature of this collision, how fast it happens, and some of the nuances. What we notice is it took 1.86 seconds to collide with sphere 2. So if I wanted, for example, that to be faster, well, if you want it to be faster, you could apply a stronger force. Stronger force could be applied not through changing the direction, because it's already, the direction is precisely as exactly towards the other object it can get. But this force here, which is 100 right now, if I bump this to, say, 500, that's 5 times the force. And if we play that now, open the console, instead of 1 second, it's 0.86 seconds. So we've halved the time of the collision, and a good thing to do would be to just put these guys on the ground to start, just so we have a better comparison. So we start out and they collide. And if we go back to our script, well, it's 0.92 seconds, so the scripted force, let's change it. It's about 1 second. If we double it now, let's see what happens. $1,000 takes us from 0.92 to 0.64. So doubling the force doesn't precisely double the time it takes, or have the time it takes to get there, because there's other stuff at work here. There's frictional forces that are default for these rigid bodies and the floor, and there's gravity at work. But the general idea is if you increase the force, these things are going to collide faster. And you can kind of tell that it's demonstrably different behavior than what we saw the first time around. So another thing that can be done here is, instead of just modulating the force by a number, by a scalar quantity, which in this case has been put to 1,000, and I can go back to 100 like I had before, is to modulate it to change the force based on the distance between the two objects. So instead of always just pushing the two objects together such that they collide and stay collided like magnets, you can modulate this force based on the distance between them. And so in other words, if we go back into our come together script here, and we calculate not only the direction but a float, which is just the raw distance, which I'll call r, between these things you get something interesting. And the distance between two objects is the square root, which is, I think it's mathf, yeah, mathf dot square root of vector3 dot rdiff, comma rdiff. So this line is saying take the square root of this quantity, and this quantity is the dot product of rdiff with itself, with rdiff again. And that means explicitly, if I were to type this out in more mathy, more obvious explicit language, it's x times x plus y times y plus z times z. This is the dot product of x, y, z with itself, and then the square root of that whole thing. So this is something you learn in geometry and algebra classes, but it's the distance between the two particles. That might be new to you, it might be super old to you. For me it's super old, so I kind of wanted to take it slow because I think it might be something worth thinking about. Because these games run on physics, so you can't really escape it at some point. That's the distance between the two particles, and then if we say, okay, well, if I want to control the force based on the distance, let's say that we have another variable called r0 or r0, and we'll assign it to 10. And I'm picking 10 because I've seen in these just play animations that we've done that the distance between the things is about 10 starting out. And now that we have distance and some reference distance, what I'm going to do is multiply this force by the difference between our distance and the reference distance. So in other words, if the actual distance is very close to 10, if it's exactly 10, this quantity is 0, and you multiply this whole thing by 0, and the force is 0, so the things don't move. At 10 meters, the things won't move. At very close to 10, they'll move either very slightly left or very slightly right. And then as you deviate from the distance of 10, the things will approach each other in opposite directions, as you'll see here. But if we use that as our force and we do the same logic in adding the forces, what we see happen is this kind of thing. So these particles we are forcing them to collide only until they reach or exceed a distance of 10 meters. Or inversely, we are forcing them to collide until they're closer than 10 meters. But once they're further than 10 meters, we pull them back together, because this r minus r naught term, when we're closer than 10, is actually a negative number, and that flips the direction of the force. So this one little parenthetical multiplier to our force, besides this thing that controls how intensely they approach each other, besides the direction itself, which tells us which direction they will move in, and besides this factor, which normalizes based on whatever the user's computer's frame rate is at, will give you this effect of a kind of harmonic motion where the two objects approach and then run away from each other. And in fact, it's called harmonic force or spring force. So that's cool. So the last thing I want to try to do in this video is not just detect collisions, not just mess with the force and how it behaves, but introduce a new particle, and instead of bringing these particles together based on the interactions of two of them, bringing them together based on the interactions of all three, and by extension as many as you want if you can just assemble your objects in a list and go from there. So I'm going to start with the simple case where I just manually add a third object. So in the sample scene, I am creating a 3D object, a sphere. We'll put him on the ground too. And let's make a new color. I bet you can guess I'm going to pick green. And I bet you can guess his name will be indeed sphere 3. So now we have three objects. If we continue business as usual, sphere 3 will be irrelevant because he's not linked or referenced or mentioned in any of the code yet. But what I want to do is bring all three of these together at the same time. If we swap our view out here, clicking on the y-axis, let's actually make it a little more symmetrical, like that. So what I'm expecting or hoping will happen if I do it right is that this red guy will come in this direction, this blue guy will come in this direction, and the green guy will come in this direction. In other words, they all will approach a center of mass. So the way to get them to do this is very similar to what we already did for the two objects, where we found out the direction we needed to go in and then just applied a force. Here the direction we need to go in is a little more tricky. Let me rename this to green. Alright, and we'll go back to sphere 1. One more thing, sphere 3 will need its own rigid body component, and I think now we are good to go. So back to sphere 1, and let's get rocking. Come together script is where all the logic is, and I'll just make this an extension of that file. So let's add a new transform so we can access the position of that third particle. Same thing, so we can apply forces to it. Here, naturally, it's just a matter of accessing that P3 object that we just added. And things are going to get a little more interesting down here. So I'm going to go ahead and remove this stuff now. And we're going to do this center of mass business and moving things together. First thing right before I do that though is I'm going to attach sphere 3 where he needs to be. So clicking sphere 1, we have these open placements for the transform and the rigid body. So sphere 3 can go on that transform, and he can also go on the rigid body. And let's go back to logic. So now we have access. We should be able to get the position at every frame, just like we were before. So center of mass is a location which is weighted not only by where stuff is, all the particles around it, but how heavy they are. So if there's heavy stuff on the right side, the center of mass gets scaled and leans towards the right. So we're going to need two things here. We're going to need to consider the mass and position of all the particles, and then, based on where that center of mass is, move all three of our particles accordingly. So, first thing that we're going to need is pretty simple, just the total mass. So the rigid body 1's mass, rigid body 2's mass, rigid body 3's mass added together. And that's a factor that normalizes out the position based on the total mass of the system. So if your total mass is 3, you divide by 3. If it's 300, you divide by 300. And you have to do that because some objects could be heavier than others. And I think you'll see why once this is through. So I think a succinct way to get center of mass in C# Unity world here would be, well, it's a 3-element vector. It's an XYZ position, just like the position of a single particle. But it's the mass of the first element times its position. So this quantity, the mass of the first times its position, is a 3-element vector. But we're going to add to that the mass of the second one times its position, and so on. So it's the sum of vectors of the masses of particles times their positions. And then finally, once you have this sum, you can just say that you divide out the total mass. So center of mass is a 3-part vector. It's the masses times the positions, all added up, divided by the total mass at the end. And just for good measure, it's good practice to just log out what you're looking at and see if it makes sense. So save that and press play. And I've removed the forces that were forcing collisions before, so everything is staying put. We look at the console and the center of mass isn't changing. That's good because nothing's moving. If I move this, center of mass is going up in Z, which is good. This should go up in X, which is good. And if we go back, wrong view, move it in Y. Oh, that was Z again. Move it in Y, and it changes in Y. And gravity's still at work, so it's fighting me. Alright, so that's great. Center of mass seems at least reasonable in terms of what I'm seeing. Now we want to move all three of these particles based on the collective center of mass. Alright, so to do that, we need, just like we had before, the directional vector between, instead of between the two particles, it's between each particle and the center of mass. So those would be dir1, we could say, is of vector 3 type, and it is the position of the first one minus the center of mass. Likewise with the second and the third. So these are directional vectors and they're not yet normalized, so we should do that with vector 3 dot normalize on all three. So that they can be used transferably. Those are our directions, and now we just need to apply forces to each of our three particles. So rigid body 1, add force. What's going on here? Add force. And we will say time dot delta time times direction 1 times, we'll call this intensity, and assign it a constant variable up here, 100, just like we had earlier. Body 2 needs a force 2, and body 2's force is going to be in direction 2, not direction 1. Body 3's force will be... I encourage you to mess with this code and change it up yourself to see what happens. Even if you break something, it's good to understand why it broke. But in any case, let's see what happens adding these forces at every step, because it's in the update function still. So we hit play. Moment of truth. So you can see these guys are moving further and further away from each other. And that is because I defined the directional vectors in the opposite direction as the center of force. In other words, these directions are position minus center of mass. If they were center of mass minus position, you'd get the opposite direction. But that's an easy fix. I could add a minus to any of these three multiplied terms here. I'll just do it on these three. And we will see, there we go, the magic of center of mass. It's a beautiful thing. And if I move one, they work hard to find themselves together. And you notice it works even if their order arrangement gets messed up, because at the end of the day, they're all just moving towards the center. And they don't care whether it's 1, 2, 3 or 1, 3, 2 as their relative positions. Okay. So if you appreciated this video, or if you have questions, or if you have ideas for other stuff that would be cool to look at and try to tackle, do let me know. Leave a thumbs up and subscribe, and I'll be encouraged to keep making some good content that'll hopefully help a lot of people make some super cool games and learn a bunch of stuff. Alright, see you next time.